Hello, we are Jussan, Tim, and Niraj. This is our final project. Today, we are going to be talking about what are the most important factors influencing the price of Uber and Lyft rides in Boston. Why do this? Rideshare prices are influenced by a host of complex factors. We'd like to hone in on the most important ones and understand them, and we'd like to see if and how weather and other objective factors impact the final price. The data set we have is obtained from Kaggle. It contains about 2 months worth of data from 2018. The features in the raw data set can be broadly categorized into two groups, rideshare specific and weather information for that day/hour. As part of data cleaning and pre-processing, we drop unnecessary columns like ID strings and time zone. We analyze and drop highly correlated weather features, keeping one if we detect pairs of almost redundant columns. Missing data. About 8% of the rows are missing a price value. As these were the only missing data in the entire data set, we felt safe to drop those rows. The final prices were transformed to log scale, and as you can see, this helped immensely with evening out the right skew of the original data. Feature selection. These are the final features we kept to train our models. It is a mix of categorical and numerical data. Worth mentioning for rideshare specific, the surge multiplier, which changes based on supply and demand. We also have weather variables, all of which are self-explanatory. We have some categorical rideshare specific columns such as source and destination, which are Boston neighborhoods the rides originated and ended in, and the type of product, Uber or Lyft, the type of subproduct within Uber and Lyft, such as Uber Pool, Uber Black, etc. And finally, we have the outcome variable, which is the price in dollars.
So in order to compare the different machine learning models, we split the data set in 80% training set and 20% test set. We run a k-fold cross-validation methodology using the training set, and then compare the mean cross-validation R-squared, which you call just CVR squared, across the different models. The R-squared gives us how much of the variance of the response variable is explained by the model. For our baseline model, we chose predicting price with the most correlated numerical features, distance and surge multiplier, through multilinear regression that's very easy to interpret and no feature transformation needed. We then obtain a CVR squared of around 0.40. From the baseline, we improved the model's complexity step by step. We decided to run the following models, including all features as shown in the table. We started by running a multilinear regression because of its interpretability, the limitation as it assumes linearity and can be sensitive to outliers. Then we run a second degree polynomial regression to capture the nonlinear relationships. And we also run a multilinear regression with interaction term to capture feature interactions. Both of these models we need to pay attention to not overfit. Fourth, we run a decision tree as it's a simple and interpretable model with the limitations of prone to overfitting and instability to small changes in the data. Then we run a random forest, which is an ensemble model that is robust and reduce overfitting with the limitation of being less interpretable. And finally, we run a gradient boosting, which it can have high performance by decreasing bias, but it's computationally expensive and it can overfit if not tuned properly. As we can observe, all models improve the performance a lot compared to the baseline and often have CVR squared higher than 0.9. We also see that polynomial model is the best with around 0.994 in terms of R squared, but nevertheless, there's a marginal difference compared to multilinear regression. So in the end, we decided to choose the multilinear regression model to move forward in our analysis. That's one of the best models with a high CVR squared. And moreover, it's the easiest model to interpret as we can check straightforward the magnitude of its coefficients.
Next, we did a lasso regression check on multicollinearity. So we used this to see if multicollinearity may have been present in the final regression model. And as you can see, the train R squared and the mean CVR squared are similar to what we achieved with the multilinear regression. So we feel comfortable concluding that there was no multicollinearity present. Next, we did a linearity assumption check. So here we checked the linearity of the relationship, homoscedasticity, and the normality of the residuals. And across all three dimensions, we feel that linearity does hold. Finally, given that the trained model passed these checks, we did the regression test, run the regression on the test data. And we see here the train R squared and the test R squared are very similar to each other. So from this, we can conclude that the model does generalize well on unseen test data, and it proves to be simple and effective for the task at hand. And here we can see the feature importance and interpretability. This is observed through 100 bootstraps. And on this next slide, we go into that a little bit further to understand it. So for example, in the product name, you have some of the lower tier cost options like Uber Pool, Lyft Shared as having a negative correlation on the price. And on the opposite side of things, you have Uber Black, Lyft Lux, etc., that are more have a positive effect on the price. And this is somewhat expected. I think some other ones you can see here is distance, that as that increases, so does the price, surge multiplier. And we found that some neighborhoods seem to have a positive correlation on the price relative to others. So strengths, limitations, high performance from the R squared for the test and trained data sets indicate strong predictive power and good generalization. It's easy to understand with clear relationships between the features and price. Limitations, we understand that there might be some minor nonlinear relationships not captured. And then also the model can be sensitive to outliers. For future improvements, we're looking at exploring hyperparameter tuning and for the polynomial regression, and also to implement a method for outlier detection. Thank you.